Consider these four rectangles. They've got widths of 4, 6, 2 and 3 respectively, and they've all got the same height, x. What is their total area? Well, by adding all of their individual areas, we can see the first one has an area of 4x, the second one has an area of 6x, the next one has an area of 2x, and the last one has an area of 3x. So altogether we have a total area of 15x. Let's now move all these rectangles together. Now we can treat them as a single rectangle, which has a base of length 4 plus 6 plus 2 plus 3, which is 15, and a height of x, so it has a total area of 15x. Algebraically, we can write this as 4 plus 6 plus 2 plus 3. All of that needs to be multiplied by x. Of course, this also gives us 15x. The important thing is that these two expressions come to the same thing. And look at how we could obtain the second one from the first one. We could look at all of the individual pieces, all of the pieces joined together by the pluses. Notice that every one of them has an x in common, and then we could arrive at the second expression, which is a factorization of the first one. We have taken the common factor of x out of all of the pieces. This is the method we need to review here. Let's see how else we can factorize common factors from expressions. In each of these examples, we have two pieces joined together either by a plus or a minus, and we need to see if we can identify common factors in each of those pieces. So, in part A, what is common to both the 5x piece and the 10 piece? Well, both of them are multiples of 5. So we could factorize out a 5 from both pieces, leaving us with x subtract 2. Because if we were to multiply this back out, we would have 5 times x, our 5x, and 5 times negative 2, which is negative 10. There's no more factorizing can be done because there's nothing both common to the x and the negative 2 term. In part B, we have to factorize 2x plus 3x squared. Now this time there is no number in common in both of the pieces. There's no common factor of 2 and 3, apart from 1, which wouldn't really get us anywhere. But there is an x in both pieces. If we factorize out an x from both pieces, the first part just becomes 2, and the second part becomes 3x. In example C, we have 4x cubed subtract 12x squared. We could notice to begin with that both of the numbers are multiples of 4, so we could factorize out a 4, leaving us with x cubed subtract 3x squared. We can then notice that both pieces in the brackets are multiples of x, so we could factorize out an x as well, leaving us with x squared subtract 3x. But both pieces still have an x as a factor, so we could factorize out another x. So we would have 4 times x, 4x squared outside the bracket, leaving us inside the bracket with x subtract 3. Now just for clarity, I've done that factorization here in 3 stages. But you could probably notice from the very beginning that both this piece and this piece have a factor of 4x squared. This first piece is 4x squared times x. This second piece is 4x squared times negative 3. So we could have immediately factorized that 4x squared out, leaving us with the x subtract 3. Example D has more than one variable in it. 6x squared y plus 3x y cubed. Let's see if we could spot the common factor in one go. Both of the numbers are multiples of 3, so we can take a factor of 3 out. Both pieces have an x in it, and the highest power of x that features in both pieces is 1, so just 3x to the 1, or just 3x. Similarly, both pieces have y's in them, but again the highest power of y that appears in both pieces is 1, so y to the 1, or just y. What would that leave us with? In the first piece we would have 2x. In the second piece we would have y squared. If you're not sure of this, just re-expand and check that you've got it right. If we did multiply the 3xy by 2x, we would have 6, 2 times 3, x squared, x times x, y, there's only one y, and indeed the first piece is 6x squared y. The second piece would be 3xy times y squared, that would be 3xy cubed, and that is the second piece. These examples contain more than 2 terms. It doesn't matter how many terms we have in our expressions, the easiest thing to do is to think of each term as a little island connected to other terms, either by a plus or a minus. So whatever may be in these little clouds is a bit immaterial really. There are some terms in there, and what we have to do is to notice common factors which appear in all of the terms. So for example, in part A we have 2x cubed plus 8x squared subtract 10x. The numbers in each term are multiples of 2, so we can factorize out 2. And every term contains an x, and the highest power of x which appears in all of the terms is just x itself, or x to the 1. What does that leave us with? In the first term it will leave us with x squared. In the second term it will leave us with 4x. And in the third term it will leave us with negative 5. In part B we have a mixture of variables, x to the 4 y cubed, subtract x squared y squared, plus 3x squared y cubed. This time there are no numbers which appear in all 3 terms, but every term has some powers of x and some powers of y. The highest power of x which appears in every term is x squared. The highest power of y which appears in every term is y squared. That will leave us with x squared y, subtract 1 because we have factorized out the entire x squared and y squared from that term, plus 3y.